So now that we have a feeling for how VSEPR works, I want to go in depth into some of the more specific rules that the theory espouses. And so the first one is that the relative sizes of various types of electron groupings about a central atom are multiple bond is bigger than a lone pair is bigger than a single bond, which is about the same size as an unpaired electron. Okay. All other things being equal, bonding electron pairs are smaller in size if the ligand atom is more electronegative. We'll see some examples of this. Why does that make sense, or how is that rationalized in this theory? You have a bond, and we know that more electronegative atoms will have more of that electron density towards them, right? Because that's basically what the concept of electronegativity is. And so if you pull more of the electron density towards the ligand away from the center, and we're talking about central atom geometry here with VSEPR, then the size, effective size, should be less. Okay? So two consequences of this. The first is that lone pairs preferentially occupy the roomiest sites in the VSEPR arrangement, okay? Because they're very big. Okay, and if there's more than one lone pair present, they will occupy the roomy sites, but as far away from one another as possible. And that, again, is to minimize electron-electron repulsion. Second ramification is that when a central atom bears a lone pair or is involved in a multiple bond, the angles between bonding electron pairs will be smaller than the ideal values for the VSEPR arrangement. And again, that has to do with this size. So let's go through some examples. So let's figure out the VSEPR geometry of this molecule, chlorine trifluoride. How do we do this? Well, we have to first come up with the number of valence electrons because we're going to draw the Lewis structure first. So we have chlorine, it's a halogen, 7, and then we have 3 fluorines. Fluorine is also a halogen, so 7 plus 7 times 3. That equals 28 valence electrons. Chlorine is the least electronegative element here. Fluorine is the most electronegative element. We know the least electronegative element usually goes in the center. And so now we're going to just arbitrarily connect these, right? We don't know the geometry yet, but we're counting electrons to help us use VSEPR to do so. And we're going to satisfy the octet rule, and let's see what happens here. We have 2, 4, 6, 8. And these are 2, 4, 6, 8 here, 2, 4, 6, 8 there. So 8 times 3 is 24. That means we have 4 more electrons we have to put somewhere. The only place to put them is on the central atom, chlorine. Chlorine can have an extended octet because it is in third row. And so what does that mean? That means that at this point, we can figure out our VSEPR geometry. How do we do that? Well, we look at the number of ligands, right? And so we have 3 ligands, 3 fluorine atoms, and we have 2 lone pairs on the central atom. That means we have a steric number 5 from the VSEPR table of steric numbers that we went over in the last video. That tells us we have a trigonal bipyramidal arrangement, but there's going to be 2 lone pairs. And so based on that, you know, there's 3 different ways that places you can put these lone pairs. And so where are you going to put them? The answer is here. It's going to be a T-shaped molecule. Why is that? Because the electrons are going to want to be as far apart as from one another as they can, because they're quote unquote big, right? And so they're both going to want to be in this equatorial site, because there you have 120 degrees angle, which is bigger than a 90-degree angle, so they can be further apart from one another. So that's right. VSEPR predicts basically anytime you have 3 ligands with 2 lone pairs, you're going to have a T-shaped molecule formed by taking a trigonal bipyramid and removing 2 of the vertices in the triangle that's in the equatorial position. Some other examples of this that can be rationalized with VSEPR theory are increasing size of lone pair. So if you go from a linear molecule, right, this cation, you have the idealized bond angle for linear, which is 180 degrees. But then if you make a radical, put a single electron here, the bond angle here is 134 degrees. And then if you put 2 electrons there, you have an even smaller angle of 115 degrees. So that shows you, the increasing size of of a lone pair. All right, let's do another example. So this is COF2. So COF2, again, we're going to come up with number of valence electrons to get the Lewis structure. Carbon has 4 valence electrons, oxygen has 6 valence electrons, fluorine has 7 valence electrons. And so 4 plus 6 is 10, plus 7 times 2, that's 24 valence electrons. Carbon's the least electronegative. And so I'm putting these in here. And what do? We're going to make an octet on fluorine. That's looking okay. We have 2, 4, 6, 8, 16, and then 20. So we have 4 more electrons left. And so what are we going to do right here? Oh, sorry, I counted. Did I count that wrong? Let's see. Yes, I counted that wrong. I thought something was wrong. 2, 4, 6, 8. Okay, 2, 4, 6, 8. That's 16. 16 plus 2 right here in the single bond to oxygen. That's 24. 16 plus 2 is 18. So we have 6 left. There we go. Okay, so I can put 6 electrons there. The problem is we don't have an octet on carbon. And we ran out of electrons. We used up these 6 on the oxygen there. So we know what to do. We put those down into a double bond. Whenever we run out of electrons, we can make multiple bonds to solve the problem. And now we have a situation where everything obeys the octet rule. Carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. And the fluorines we already counted have 2, 4, 6, 8. We have 24 valence electrons. What is the VSEPR geometry? Well, it's trigonal planar. We have 3 ligands, right? 1, 2, 3, and no lone pairs on the central atom, so that's trigonal planar. What about the bond angles? Well, idealized bond angles should all be 120 degrees. But we know that a multiple bond from our rules that we went over occupies more room. And so that's going to cause the bond angle to expand for the fluorine-carbon-oxygen bond, and correspondingly going to cause the fluorine-carbon-fluorine bond to contract. So this value is less than 120, and this value is greater than 120. How do we compute the actual values? We cannot using VSEPR. Let's do another example. POF3, very similar idea here. Phosphorus is the central atom. It's the least electronegative. So I'm going to put that in the center and connect these. But before I did that, I'm kind of getting ahead of myself because I should have calculated the number of valence electrons. Phosphorus is in group 5, oxygen is in group 6, chalcogen, halogen, or fluorine is 7. And so what are we at there? 21 plus 6 is 27, 32 valence electrons. And we go ahead and put everything down and give it an octet rule, and that's going to be good. 2, 4, 6, 8, we're good. And 8 plus, they're all kind of equivalent here, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. 8 times 4 is 32. So that's good. So what's our VSEPR geometry? It is going to be tetrahedral. We have 4 ligands, right, and no lone pairs. But just to show you the bond angles, similar type of thing as last example. Again, you have a multiple bond here, a double bond here, that's going to take up more room. And so although the idealized bond angle is what? Is 109.5, the actual number here is 113. It's greater than 109.5, and the phosphorus fluorine bond angle, fluorine phosphorus fluorine, is less than 109.5. This multiple bond takes up more room. Let's keep going here with another example. And so we're going to again think about valence electrons. This is a methyl group, so that's going to be, I'm not sure why there's that weird thing there. That's going to be CH3, and so 3 of them, and fluorine there. Okay, very good. Hydrogen we know is going to be a terminal atom. It's going to be in these methyl groups. And so we can get our connectivity here before we calculate valence electrons. It's going to look something like this, right? We have 3 of these connecting to a carbon. Hydrogens can't connect with multiple things. And then we have fluorines and fluorines. And so our total number of valence electrons, and if we really wanted to be, super clear on this when we count, it may be easier for me to actually write out all these hydrogen bonds. But we know how those are going to be. They're going to be like that because it's following the duet rule for hydrogen, right? So as drawn, all these are good. They're all following the duet rule for hydrogen. So if I total count the total number of valence electrons here, what am I going to have? Phosphorus has 5. Carbon, well, there's 3 carbons. Carbon's in group 4, so times 3. And how many hydrogens? There's 9 hydrogens. Hydrogen is in group 1, times it by 9. So 9 of them. Fluorine is a halogen, so there's 7 and 2. And so we're going to have 5 plus 4 plus 12, 17, 17 plus 9, excuse me, is 26. 26 plus 14 is 40 valence electrons. Let's see how we do. How many do we have on the board right now? We have, well, let's just count the number of lines. Okay, each bond has 2 electrons. So we'll just count the number of lines and multiply by 2. 1, 2, 3, 4. There's another 4 here, 8. Another 4 here, 12. 12, 13, 14 times 2 is 28. Okay, so 28, and we're left with 12. Let's put them down. Put 6 there and 6 there, and look at that. That all works. We use 12. Good. So that is our structure. So now we know we have around phosphorus, we have 1, 2, 3, 4, 5. 5 ligands, no lone pairs. That's going to be a trigonal bipyramidal setup. Phosphorus has an expanded octet. Octet here, but that's okay. It's in the 3rd period, so it can do that. Now the question is, we know it's trigonal bipyramidal. Which of these, where do we put the fluorines and where do we put methyl groups? We have 3 different options, which I've drawn here. Which one is it going to be? It's going to be this one. The methyl groups are bigger. They're 4 atoms versus 1 atom on the fluorine, and so they're going to occupy the roomiest site. As we said with the previous example, the roomiest site is in the equatorial position, where there's 120 degrees separating the atoms, versus in the axial, there's only 90 degrees. So this is actually the experimentally observed structure of this compound, not these other isomers.